Hello my dear students, this is Akash SD and welcome to the ASD Physics classes. So students, I hope so you are regularly watching videos on my channel, especially the parts are going on acceleration due to gravity. Till now I have made the 2 parts and this video is going to be the 3rd part of the same series. And now please listen very carefully. Tomorrow evening some 6:45 PM I am going to conduct the live classes for the same portion, acceleration due to gravity, and it is going to be the part 4. And in that what I will do, I will discuss the questions from NEET exam and JEE exam. Now very important questions will be there. That's why this video is very important. Just see it very properly. Okay, so students, in this video we are going to learn the theory part of the variation in acceleration due to gravity. Okay, so let's see one by one here. First thing, see here. First variation is what? Due to height above the surface of planet. And whenever I will use the term planet, no? So this planet means, most of the time this planet means Earth only. Okay, so if sometimes I am using the term Earth also, that is for the planet. Planet means Earth. So both are interchangeably I will use it. Okay, good. Second one is here, please. Due to depth below the surface of the planet. Third one we are going to see due to the shape of planet, and fourth one I am going to see due to axial rotation of the planet here. Okay, and I hope so in our previous videos and all you have learned very well the gravity value, that means acceleration due to gravity value on the surface of the planet. How much here? This value I will use it here, G equal to Gm by R square. Okay, where M is the mass of the planet and R is the radius of the planet, and this small g is the value of acceleration due to gravity on the surface of the planet. So wherever I am writing g means the gravity value on the surface of the planet. Okay, please make sure very well here. For other things and all, here I will use gh, gd, gs, and here gr I will use it now further. So let's go to the first one here. What is this? Due to height above the surface of planet. So say here, let the observation point P is at a height h above the surface of a planet of mass capital M and radius r as shown in diagram. So here I have just taken one spherical planet I have taken here. So see here, please, here its mass is how much here? M, and its radius how much here? This radius is r. And here I have taken one observation point P. How much height? This observation point is having height h. Okay, so you think, please, this is h, this is r, no? And this is the center. This is the center here. Center to the observation point. Center to the observation point is always given by small r here. Now, see here, please, here. Center to observation point, how much here? Small r. So this is h, this is r, and total is small r. So we can write here small r equal to how much? R plus h. Okay. So this is my observation point P. So students, at point P, the gravity value at some height, that means gh, is given by in the same way. What is that? Gm by small r square here. Okay, and what is small r? Small r is r plus h. That means I can write here, see please, Gm by r plus h whole square here. Okay, after that if we do the comparison, that means comparison of the this gravity value to the surface value. So if I write here, see please, this gh by g. So what is gh? Gh is how much? Gm by r plus h whole square. And what is g? Gm by r square. So gm will cancel out. That means I can write here, see please, r by r plus h whole square here. Now this is the exact formula is there. Now after that, what is there? We have to learn one approximate formula also, because sometimes the height will be not that much. So that time we have to use the approximate formula here. Now, so let's see here, please, the third one we are going to see which formula? Approximate formula here. Approximate formula. And in which situation we can use this approximate formula? This approximate formula will be valid when what is this? When this h is less than r. Okay, and especially if we talk for the earth, if I talk for the earth, then what will happen that here? This h should be less than 320 kilometer. If we are talking about the earth, h should be how much here? Less than 320 kilometer here. Now in that situation only we can use the approximate formula here. So see here, please, here we can write here, see, gh by g is equal to 1 by, now this r I will take downward, so it will become here 1 plus h by r power 2, and then it will become here, see please, 1 plus h by r power minus 2 here. And if I will use the binomial expansion, because h by r is very, very small, then I can write here, see please, this gh by g is equal to 1 minus 2h by r here. Now, so this is the which formula? Approximate formula when h is less than r. And for the earth, if we talk especially for the earth, that means h should be how much? Less than 320 kilometer. Okay, so this is all about what? This is all about the height. Now, after that, if I draw graph also, see here please here. Graph also, see here please here. No, graph. No, I am drawing the graph here. See, this side is gh and this side is r. Okay, so tell me please here, when we are on the surface of the earth or the surface of the planet, then value of small r will be how much? The value of small r will be how much? Capital R here. Okay, so on the surface of the planet, small r is capital R here. Na? So this is outside. So what we can see here, this is inversely proportional to r square. You can see gh inversely proportional to r square. Then how the graph will be? The graph will go like this here. This is the GH versus R graph here. Okay. If I draw one more graph is there. Now this is the one graph. If I draw one more graph is there. Sometimes the graph can come like this also. This side is GH and this side is H. Is it? So at the surface of the planet, the H value how much here? 0. And at the surface value how much? G. So then the graph will be like this here. Now, so this is GH versus R and this is GH versus H. And H is what? The height of the observation point from the surface. Okay, so this is the height here. After that, students, let me go to the second one here. Due to depth below the surface of planet. So see here please here, let the observation point P is at a depth D below the surface of a planet of mass capital M and radius R as shown in diagram here. So now what I am going to do here, I am going to take one observation point here. Now observation point P. Okay, observation point P at how much depth? This is at a depth D here. Now, and again I am telling that here, again the mass is M and the radius how much here? This radius is R. Okay. Now what will happen that here, whenever it comes to the depth through the observation point here, we will draw one sphere passing through it here. Now like this here. Now, so this is like this. Now this is the inner sphere, and let's take this inner sphere is having mass m dash and the outer sphere. This is the outer sphere here. Let's take this one here. Not outer sphere actually. We can tell the outer shell. Outer shell. So you have to remember that one thing. This observation point P is inside this thin shell. Now, so whenever the observation point is inside, then this outer shell will not exert any gravity, any gravitational force at point P. That means due to the outer shell, there is no gravity, no acceleration. So gravity will be due to which sphere? This will be due to inner sphere only. Okay. Even this thing you will learn in a class 12th. That the topic will be this Gauss law here. Okay. So please remember that here. Here the gravity will be due to which one? The gravity will be only due to which one? Only due to the inner sphere here. Okay. So again I am telling that here, as the observation point is where? Observation point is where? At the surface. That means total mass can be concentrated where? At the center here. How much mass? M dash. And see here please, this is point P here. Now, and this value how much here? This value I have taken small r. Now center to the observation point here. And if you will see that here, this small r will be how much here? R minus D. Okay. So now, due to mass m dash, gravity at point P is given by here. Now again let's see here please students. So see first one please. So gravity at depth D is given by G m dash by R square. But now we have to find out this m dash value. And to find out this m dash value, what we will do? We have to use the unity rule here. Now, unity rule. So please remember that here, this m dash value is given by mass per unit volume of complete sphere into the mass of the inner sphere. Then what will happen? 4 by 3 pi, 4 by 3 pi cancel. Then this m dash value will come how much here? This m dash value will come m into small r cube by capital R cube. Okay, this m dash value I will replace here. Now, so when I will replace this m dash value here, what this will come here? Again I am writing here, see, this GD is equal to what to tell? G by R square, and here m dash value m into R cube by capital R cube. Is it? So again this R square will cancel out. Then what it will come here? See please, it will come here Gm into R by R cube. Now, so this is one form is there, and here you have to remember that here this GD value is directly proportional to R. This GD value is what? Directly proportional to R. So see here please, here if I draw one more graph here, see here please, this is the GD and this side is R. Now this side is R. Then what will happen at here? At the surface, a smaller value how much here? Capital R. So see here please, here what is there? The GD is directly proportional to R. That means the graph will go like this. The graph will go like this here. Now, so this is the gravity due to depth and this is small r. What is small r? The center to the observation point distance is there. Okay. So this is one part is there. After that, if I talk about the second one, see here please, again second one, see. Now, so students just see here the second one. Again, we know this GD equal to how much here? Gm into R by R cube. And what is smaller value? Capital R minus D. Okay. So I can write like this here, Gm by R square, and here smaller how much here? R minus D by R. Okay, and what is Gm by R square? I have told in the starting of the video G. So we can write here, hence this GD is equal to G 1 minus D by R. Okay, so this is one more form. One more form. And please make sure that this form is very similar to which line? Y equal to mx plus c line. So if in case I draw the graph between G and D, this is GD and here D. So see here please, here the depth value how much here? Here the depth value will be 0 here. So when the depth value is 0, that means where we are? At the surface of the planet. That means G, and when this depth value is equal to capital R, where we are? At the center, and at the center the gravity value how much? 0. So if we connect both these points, we'll get the graph like this here. This is which graph? The gravity versus depth graph is there. Now please make sure it very well here. Okay. So now students, we have seen the height, depth, and next one we are going to see the shape of the planet. So see here please, due to the shape of the planet, the earth is not a perfect sphere. It is somewhat flat at poles. The equatorial radius is how much? Approximately 21 kilometer more than the polar radius here. Now that means earth is not a perfect sphere here. See, here I have taken the earth, but what is this? This is not a perfect sphere. Now, so let me make it somewhat imperfect here, like this. Now, like this kind of situation is there here. Now, like this here. Now, like this. So here what will happen that here, if we talk about here, this thing here, this is called what? This is called the equator here. Is it equator? So if you see here, this radius is called which radius? Equator radius. And similarly, now this is the equator, and what is this? This is the pole. Now, and this is which radius? This is the polar radius here. Now, so you can see very well here, the RE is greater than RP. Okay, so what I'm telling here, what is this? The RE is greater than RP. Now if I write here the gravity value on the surface, how much formula? Gm by R square. So from here we can tell this G is inversely proportional to R square. That means as this RE is greater than RP, hence this gravity at the equator is less than the gravity at the pole here. So sometimes they used to ask that when the person is traveling from equator to pole, then what will happen to the weight? As the gravity will increase, so weight will also increase. And if in case the person will go pole to equator, then what will happen? The gravity will decrease, and then what will happen? The weight will also decrease. Okay, please remember that here. Now after that we'll go to the next one, please. Let's go to the next one here. Now see here please. Due to axial rotation of the planet. Now, so let's see here please. Let a planet of radius r is rotating on its own axis with angular speed omega, and the observation point P is on the surface of planet at latitude lambda as shown in diagram here. Now, so here I have drawn somewhat bigger diagram because the diagram is going to be very, very crowded diagram here. Okay. So see here please, this is the equator here. This is the equator. This is the equator here. You know very well. Equator, let me decrease it somewhat now, and after that, see here please, here the earth or any planet, no problem, it is rotating with angular velocity omega. Okay, so now please make sure that, let's take, here is the observation point P. Okay, so if in case what will happen that at this observation point, if I put some mass m, now I have taken the test mass here. Now, so what will happen that here, this mass m will also rotate in a circle of how much? This one will also rotate in a circle of radius r. Okay, And see here, please, here from center to this distance is how much? This is capital R. So what will happen that here, this test mass, it will experience one force mg. This mg will act in which direction? This mg will act towards the center, is it? And as this particle, this test mass is moving in a circular path, and earth is what? Earth is a non-inertial frame here, is it? Non-inertial frame means it is having some acceleration. Okay, so here what will happen that here the particle will experience one force in which direction? In the outward direction. That is called which force? That is called the centrifugal force, and it is given by here mr omega square. Okay, so just let me draw here the equivalent diagram here. Now at point P, I have taken point P. Now here what is this? This is the mg is there. Okay, and here mr omega square is there. Okay, so students, after that what will happen that here, let's take this angle. This angle how much here? This angle is lambda. This is called which angle? Latitude angle. Especially when we are at the equator, this lambda value will be 0 degree. And if in case we are at pole, where we are at pole, then this lambda value will be how much here? 90 degree here. Okay, so here I have taken this equivalent diagram here. Then after that, see here please here, if this angle is lambda, what about here angle? Here angle how much here? This angle also lambda here. Now let me draw here. This angle how much here? The lambda here. Okay, so now this side component how much here? This side component how much? Tell me please here. No? So this side component will be how much, students? mr omega square cos lambda, is it? So now at point P, the resultant force, no? So mass into gravity mgr, that means due to rotation, is given by mg minus mr omega square cos lambda, is it? Even this is called sometimes effective weight also. So m will cancel both the sides, that means we can write here this gr equal to g minus r omega square cos lambda. Do you think is there any relation between small r and capital R? Yes, you can see one triangle here. Now see, if I draw here one triangle like this here, see, this is a small r, this is capital R here, is it? And this angle how much? This angle is also lambda here, this angle also lambda, is it? So if you will see from here, this small r by capital R will be how much? This will be cos lambda here. Now, so this value let me put here. So if I put the value here, then what will happen here? See please here, this gr equal to g minus r omega square cos square lambda. Here the small r value I have put how much here? This one, capital R cos lambda. So this is the general formula of the acceleration due to gravity due to the rotation here. Okay, so here what is there? The 2 points are there. You have to remember that when we are at equator, where we are at equator, at equator what will be there? The lambda value how much? At equator lambda value will be 0. That means due to rotation at equator, no? GRE is given here, no? At equator. So it will come here what? G minus R omega square cos square 0 degree here. No? So what this will come here hence? This GRE is equal to G minus R omega square. This is where? This is at the equator. Okay. Now after that, if I talk at poles, where? At poles. So just think please, at poles lambda value will be how much here? At poles lambda value will be 90 degree. That means we can write here the gravity due to rotation at pole is given by G minus R omega square and cos square 90. Cos 90, 0. That means the gravity due to rotation at pole is given by G. Is it? That means what we can see, the acceleration due to gravity at pole is independent of the rotation of the planet. But the gravity value at equator depends upon the rotation of the planet here. Okay, so please remember that here. After that, next one we'll say here, see, the condition of weightlessness of an object on the equator. So can you tell to me here, the weight means mg, mass cannot become 0, then what will become 0? The gravity should become 0 here. Okay, so but before that, for the weightlessness condition, again I'm telling, this weightlessness condition is what? The gravity due to rotation at equator should be how much? 0. This condition we are going to use here. So see here, we know that GRE is given by G minus R omega square. Let's make the gravity value 0. So 0 equal to G minus R omega square. Again let's simplify this here. So omega will come here, root R by G here. No? So if the planet is rotating with how much speed? This much speed. Then all the objects on the equator will become what? They will become weightless. Similarly, if we talk specifically for the earth, then what will happen that here, this omega will become what? Root RE by G, okay? And this value will be 17 times of the present angular speed, okay? And this should be how much here? 1 by 800 radian per second, okay? So this is for the earth. Similarly, if I talk about the time period, what I'm talking about, the time period. So what is the current time period of the rotation of the earth? 24 hours here. But if we want to make all the objects on the equator weightless, then what should be the time period? The time period will become here t equal to 2 pi by omega. Put the value of omega. How much value? It will come actually G by R. No? And here also how much here? This G by RE. Okay, now we are going correct here. So what this will come here? T equal to 2 pi root RE by G here. Okay, and this value is used to be how much? Please remember that here. This value is used to be 1.41 hour or 84 minutes. Okay, so dear students, in today's video, what are the things we have learned? We have seen the variation in the acceleration due to gravity, due to the different factors. Okay, so this is the part 3, and tomorrow evening 6:45 I am coming with the part 4, and I am going to discuss the very important questions of NEET and JEE exams related to this topic. Okay, so students, if you have understood this video very well, just kindly comment, share and subscribe to my channel. Okay, thank you so much.